Hello, everyone. My name is Gal Oren, and I'm with the Technion and NRCM. Here with me is Kfir Tzvi, a researcher at IAEC, and currently a master's student at Ben-Gurion University. Today, we will present our novel optimized memoryless fair share HPC resource set scheduling using transparent checkpoint restart preemption. So what are we going to talk about today? We will start with some intro to the related HPC and supercomputing problems in regard to scheduling. Then we will move to what we call the ideal scenario, in which we explain what we want to change in the current scheduling methods in supercomputers, and also to present the related work already done in this regard. Finally, we will propose our new method, discuss the pros and cons, and introduce some implementation dilemmas. Let's start with some intro to the problem from the HPC perspective. In recent years, the demand for HPC resources has been rising drastically. As a result, HPC resources have been made available over the cloud. One example of a cloud service which provides access to HPC resources is AWS, Amazon Web Services. It can be accessed through a service named Parallel Cluster, and it even allows to use common resource managers such as Slurm. So why shouldn't supercomputing or the entire HPC community just migrate to the cloud? Well, first of all, HPC on the cloud is limited since cloud hardware is built for general purpose applications and is not tailor-made like a supercomputer. Hence, it is insufficient for large-scale coupled computations. Moreover, the current commercial tariff paradigm makes it more expensive to run continuous computation on the cloud compared with on-premise resources. Still, on-premise system has a major disadvantage. Unlike the cloud, which its economic model allows to dynamically assign resources, on-premise supercomputing facilities are forced to use static partitions in many cases. These partitions usually originate in certainly managed work plans and reflects the entitlements of each user or group over the system. The problem is that they limit each user or group from using other partitions' resources, and by that result in underutilization of this very expensive facility. The more users and partitions, the less utilization and productivity. For example, in case of two users, each one with its own partition, we can see that fragmentation is formed due to the fact that each user is not using its own partition at all times. These unused resources go to waste, and the system stays underutilized. To mitigate this problem, constant adjustment in system priority has to be made, which is far from ideal. This problem is getting even worse as we move ahead to the exascale era this or next year, as there will be more users and more compute power that will increase the underutilization of those extremely expensive systems. A possible approach to deal with this problem is to develop more effective scheduling methods that consist of job queues. Supercomputer job queues are among the most visible and often discussed productivity problems in HPC. There is a tension between users, many of whom certainly dislike time lost while waiting, and centers whose funding is at least partially justified by maintaining high utilization of their systems. In our own research and long-time work in the field of supercomputing, we have come across many instances where queue wait times have drastically inhibited productivity. Our findings are also supported by this well-attended Birds of a Feather session at the Supercomputing 2006 conference, which was held to discuss current scheduling policies at major centers in terms of their productivity. A lot of time has passed. Unfortunately, not much has changed, and current scheduling methods still do not solve the problem. In this presentation, we will introduce our new approach to tackle this problem using recent advancements in the field of OS. Now that we understood part of the problem, let's move on to our ideal scenario of scheduling, which is to bridge the gap between on-premise and cloud scheduling in the most effective and transparent way.
As previously mentioned, in the current state, users are each assigned a static partition and cannot use any others. We would like to remove this barrier and to enable resource pooling. so that the whole system can transparently be used by any user according to its claim overlay. In this example, user 1 is entitled to 70% of the system and user 2 to 30%. Note that the resources are no longer partitioned statically. The fact that the user is entitled to a certain amount of resources doesn't necessarily mean that it will use all of it at all times. In this case, user 1 uses only 40% of the resources it is entitled to. Obviously, we wouldn't want the resources to go to waste, since as long as they are unused, other users can use them. In the event user 1 wishes to use its resources once again, we need to allow access to them instantly. Therefore, we will preempt user 2's job and allow user 1 to run. We will do the same if it wishes to use all of its resources. Eventually, user 1's computation will finish. In this case, we can transparently resume the preempted jobs and let them keep running. Note that although in this case the job resumed on the same resources, it is not mandatory. It can also be resumed on other resources. What we have presented here is the ideal case, and it obviously ignores many issues and technical limitations that we will tackle later. First, let's review some related work. The first work we are going to talk about is the basis for our work. In this work, Rodriguez et al. Have integrated a checkpoint restart library named DMTCP into a well-known resource manager named Slurm. By doing so, they basically allow to transparently preempt any job that is running through Slurm without any data loss, assuming that it is supported by DMTCP, of course. Let's cover what DMTCP and Slurm are. DMTCP is a library that is used to checkpoint and restart applications. In other words, it allows to pause a running program by saving its entire state to persistent storage, so it can be later resumed by loading the data from the storage to the main memory. DMTCP is a system-level library, which means that it saves the state of the program over the entire system, which includes open file descriptors, open sockets, and other OS artifacts. It works in user space, giving it the portability to run on many kernels without any modifications. In addition, it needs no admin privileges. DMTCP works by injecting a shared library into a program and wrapping its system calls with hooks. This way, DMTCP can monitor the actions taken by the application and to save them. It is only possible when running the program with DMTCP in advance. To get you into a bit of perspective, let's review the various levels of checkpointing and where DMTCP stands. In the following table, we can see that checkpointing can be done in 4 levels: application, user level, OS level, and hypervisor. To perform checkpointing in the application level, one gains a very small overhead along with a small checkpoint image. However, since the source code of each program has to be modified to checkpoint the needed data, one has to deal with a very high implementation cost, let alone maintenance as the program evolves. In practice, application-level checkpointing does not work in the long term. In cases it is used at the beginning of the application development cycle, it is usually neglected along the way. The other levels are usually transparent, but try to checkpoint the entire system from the application's point of view, resulting in a bigger image size. So why was DMTCP chosen for checkpointing? First, unlike application-level checkpointing libraries, it requires no source code modifications. Maintaining the checkpointing code of each application is difficult, and transparency resolves the issue. Second, by working in user space, DMTCP doesn't require any installation, and it can be used on many Linux distributions. Third, it supports many key features, which speed up programs' execution time. Among them are features such as system v shared memory, which is used by many MPI implementations, and InfiniBand. Last, it supports parallel or distributed applications, which are the main focus in HPC systems. CRIU, for example, although promising due to the support for containers, still doesn't. So now that we got to know DMTCP, let's review Slurm. Slurm is an open source cluster management and job scheduling system, which is used in both small and large Linux clusters. As a resource manager, it manages the access of users to system resources and assigns each user a job, which is a set of nodes allocated for some time duration in which the user can use them to run its computations. Slurm has started, as its name suggests, as a simple utility. However, nowadays it also includes an internal job scheduling system. Moreover, Slurm is plugin based, making it easily extendable so it can support new scheduling methods. As none of the other resource managers provided full support for a checkpoint restart library, Rodriguez et al. Have chosen Slurm because of the easier extendability using plugins, and because of its vast use in the top 500 supercomputers list. In general, they made Slurm run each program with DMTCP via a shell wrapper, so it can capture the program state at constant time intervals, making each program run in Slurm preemptible without any data loss. They have also developed two sample scheduling algorithms, which we will not cover in this presentation. Next, we will talk about fairness. Fairness is an attribute of a job scheduling system. It ensures that each user in the system gets its fair share. It is of utmost importance to HPC users, probably even more than the utilization of the system. In our context, we will refer to fairness as a state in which each user has a certain level of resources to which it is entitled, and it gets at least this level. In regard to how we make sure that each user gets the level of resources it is entitled to, a distinction is made between history-based fairness and memoryless fairness. Let's review the definitions with a demonstration. For this purpose, we have a user with 70% of the system and a user with 30%. As before, a user does not always use its full entitlements. In history-based fairness, we will keep track of its resources over time. For each user, we will introduce a meter. This meter keeps track of the resources used by each user at any given moment. Next, we will introduce a pointer for each meter, indicating the average level of resources used recently. For instance, over the last month or so. Let's start counting the time. In the current state, the pointers point exactly to the level of resources used by each user. Hence, in the next timestamp, they will not change. Now, let's say that user 2 is willing to run a computation on account of the unused resources. Since we want to increase system utilization, we will allow it. The meter of user 2 is updated accordingly. And as we move on to the next timestamp, it will be updated again. And after another timestamp, it will be updated again. After some time, user 2 will finish its computation. Note that now its pointer indicates that recently it has used more resources than it is entitled to. Now user 1 is willing to use all of its resources. It is even willing to use more resources than it is entitled to. Since user 2 has been using more resources than its entitlements, now we will give user 1 priority. We will preempt user 2's job to allow user 1 to run. As time goes by, their metrics will even to their entitlements, in which point we will let user 2 use all its entitlements once again. So to recap, history-based means reprioritizing jobs according to previous job metrics so that over time, this metrics reflects their user entitlements. On the contrary, we have memoryless fair share. In memoryless fair share, we do not keep track of any job metrics. Instead, we divide the system resources at any given moment according to active demand by users and according to their entitlements. We think that memoryless fairness is the better approach, but it hasn't been possible until recently. Let's review common scheduling methods with Slurm as a case study. Slurm has two main scheduling methods that come built in. The first one is a simple first come, first serve. In this method, the jobs that are submitted to Slurm are assigned resources in the order they are submitted. Each job is assigned a reserve time, representing the time it is supposed to start. In order for Slurm to schedule the jobs, the users are required to give an estimation for the time each job will run. These estimations have been proven to be highly inaccurate as users tend to overestimate, which results in poor system utilization. The second method, used in Slurm as well as in other resource managers, is called backfill, and it is basically an extended version of FCFS. This method tries to overcome the poor system utilization by trying to schedule jobs in blank spaces between jobs runs. This way, it does not cause any delay to jobs at the top of the queue, which keeps the system fair. Although it is the best solution available today, it still does not solve the problem of users' overestimations. In this case, we can see that job D could be scheduled in the space between A and C if its runtime estimation was more accurate. However, it is not possible since the scheduler cannot know this in advance, and it must not cause a delay to job C. We could solve this problem only by using checkpointing, in which case job D could be scheduled along with job E, and as soon as job C will need the system resources, a checkpoint could be used to evict job C and D to be later restarted. We can see that in the diagram. Now that we have covered all that was necessary, let's present our solution. The optimized memoryless fair share HPC resource scheduling, or in short, OMFS. According to our proposed solution, each entity in the system is guaranteed its CPU entitlement, so it can use it instantly at all times. Instead of using static allocations, resource pooling is used, so that jobs are no longer limited to certain compute nodes, and can now migrate between them mid-run. In case there are unused resources, they are distributed among users with active demand, enabling them to use more resources than they are entitled to. In order for it to be possible, each computation has to be either preemptible or checkpointable. In the case of preemption, there will be data loss, whereas in the case of checkpointing, the system will save the application state and will be able to restore it later. In this regard, users will be able to run non-preemptible jobs only up to their entitlement, so the jobs that exceed the user's entitlements can be evicted whenever necessary. Let's move on to the pseudocode. The code consists of 4 procedures: system init, which is run only once at startup; job init, which is run for every job creation; the memoryless fair share scheduler, which indefinitely dequeues jobs from the queue; and the fair share runner, which contains the core logic of the algorithm. The system init procedure gets as an input the list of users in the system and 2 priority queues. One for submitted jobs, which includes both jobs that have been started or jobs that have been preempted, and one for currently running jobs. We set the total number of CPUs in the system, as well as initialize the amount of idle ones. Next, we keep the users, the submitted jobs queue, and the running jobs queue in internal variables. Then, we make sure that each user gets a valid level of resources over the system. Also, that the total entitlements over the system does not exceed 100%. That wouldn't make sense. An important note regarding the jobs queues is that they can be anything. We do not want to limit the system owner, so they can be thought of as an abstract priority queue that could be implemented as a simple FIFO queue or as anything else. The job init procedure is run for every job creation, and it makes sure that each job is assigned a valid priority, a CPU count, and a user. The scheduler method is quite simple. It constantly dequeues jobs from the submitted jobs queue and transfers them to the runner procedure. Now we move on to the runner procedure, which contains the core logic of the scheduler. We will go over it part after part. The procedure starts with some variable definitions. The first one stores the amount of CPUs held by the user's preemptible jobs. Then we store the amount of CPUs held by non-preemptible jobs. We calculate their sum to get the total CPU count for the user, and then calculate the amount of CPUs the user is entitled to. Next, we move on to perform some tests to determine whether or not the job should be scheduled. The first test checks if the current job makes the user exceed its entitlement with non-preemptible jobs. As we have stated earlier, we do not want to let that happen since then we will not be able to evict any job in case it is necessary. Therefore, in this case, we enqueue the job back to the submitted jobs queue and return. Next, we want to check if there are enough idle CPUs in the system for the job to run. In case we do, we want to let the job run anyway to increase the system utilization. So we go to line 37, which enqueues the job to the running jobs queue and update the amount of idle CPUs in the system. If we don't have enough resources in the system, we need to check whether or not the user is entitled to run the job. In case it isn't, we return as before. In case there are not enough resources and the user is entitled to run the job, then we want to evict jobs from the system to make resources available. We will run in a loop that preempts jobs one after another until enough resources are free. In case the job evicted is checkpointable, we will return it to the submitted jobs queue. Otherwise, it will be stopped entirely. After enough resources are free, we will enqueue the job to the running jobs queue and finish. Many issues arise from our proposed solution. Here, we will cover the main ones. The first major issue we have to deal with is thrashing, caused by recurrent CR preemption operations. In the worst case, we will have a user that is running a very large job on the system that exceeds its entitlements. In this case, any user which submits a job, even a small one, will force the large job to be checkpointed entirely. We will then let the small job run since it's within user 2's entitlements. Next, it will be finished, and then we can resume the large job. The real problem is that user 2 can submit small jobs repeatedly, increasing the overhead of the CR operation significantly, resulting in poor system utilization and a waste of resources. We will address this issue with two approaches. The first one is an algorithmic solution. We will let each job to run for a minimal constant time duration, often referred to as quantum, before we will allow it to be preempted. There is an obvious trade-off between the interactivity of the system, which is very important, and the CR overhead. We will try to find the optimal quantum to keep both the users happy and the system highly utilized. Another approach we will take is to use recent developments in non-volatile RAM to reduce the overhead incurred by CR operations. NVRAM is an intermediate layer between traditional volatile RAM and persistent storage, such as SSD or a plain old hard disk drive. This approach is valid as some new exascale supercomputers like the Aurora support NVRAM. NVRAM can be used in several ways. The first one is to use it as a storage device, exactly like a normal disk. In this case, the communication will be performed by a file system and a driver, and each access to the NVRAM will be performed by blocks of memory, often referred to as pages. Another, much more efficient approach is to use NVRAM with either persistent memory-aware file system or direct access. Both approaches are byte addressable, meaning that we could access the storage in a resolution of a single byte instead of blocks of memory. With the PM-aware file system, we can use a special file system that knows how to access the NVRAM byte by byte. This way, we get transparency from the application's point of view. However, this does not come without a cost, since several copies of the data have to be made when working with the file system. A more efficient approach is to use the NVRAM directly, using a dedicated library such as Persistent Memory Development Toolkit, also known as PMDK. In our context, the application is DMTCP, which is the CR library that is in charge of the read and write operations of the checkpoint images from memory. If we use direct access to the NVRAM, we will have to modify DMTCP to use PMDK for reading and writing checkpoints. Let's view a demonstration of how this is performed. With PMFS, a checkpoint is first transferred from RAM to the file system, and only then it is stored in a file on the NVRAM. The same goes for restoring a checkpoint from the NVRAM. With DAX, direct access, we do not have this intermediate step, and we use the NVRAM directly. In this case, we use PMDK as a bridge that connects between the RAM and the NVRAM, and we can use it to perform read and write operations. There are still some open topics that we have yet to decide how to resolve. The main one is regarding to how to distribute unused resources among users. Should we keep it as simple as FCFS, or should we strive to distribute them fairly as well? There are some more that, due to lack of time, we will not present here. To conclude, we presented the optimized memoryless fair share HPC resources scheduling using transparent checkpoint restart preemption. We keep the status quo regarding the fairness of the resources distribution, which is crucial to the user's work fashion, while maximizing the ability of all users to achieve more CPUs and CPU hours for longer periods of time without any non-straightforward costs, penalties, or additional human intervention. As part of the development of our scheduler, we intend to test it on the Negev HPC semi-supercomputer cluster. We will start by building it as an external scheduler using Feisler and evaluate users' behavior. Later, we will build a dedicated Slurm plugin based on the work of Rodriguez et al. And apply our solution to the thrashing problem using NVRAM. We hope that this presentation has been clear and that we have managed to make our point. In case there are questions, feel free to contact us.